so it's my great pleasure to introduce the second speaker of today, Jérôme Poineau from the University of Caen, Université de Caen, Normandie. He's going to speak about Berkovich spaces over Z and Schottky spaces.
Yes, so first say thank you very much for giving me the opportunity to talk here. I mean, it's and many thanks to the organizer for putting this up. I think it's very nice to have such an event still going on, and it's very nice and a great way to remember Alexey. So I'm going to speak about Berkovich spaces over Z and Schottky spaces. Whoops, yeah. So here's what I plan to do. So first, I'll begin with reviewing briefly what's known about uniformization of curves, first in the complex case, but also in the non-Archimedean setting. And then my second part is going to be about Berkovich spaces over Z. So there are, just roughly speaking, some spaces that contain naturally at the same time complex analytic spaces and p-adic analytic spaces. And then I tried my third part to mix everything, so uniformization of curves over different valued fields, and how are you able to put that all together? And I try to talk about a few applications towards the end. So first, uniformization of curves. So I think this dates back to to the work of Koebe in the complex case, 1907. So well-known theorem by now, of course, that tells us that up to isomorphism, there are only three possibilities for a universal cover of a compact Riemann surface, either the projective line, the affine line, or the open unit disk. So that's a complex case, and it's actually quite specific to it. So we may wonder what happens in the p-adic setting. So before trying to reach a solution, a full solution in full generality, let's start with the probably most well-known case of elliptic curves. So over C, it looks like that. Basically, so if you take the C point of an elliptic curve, we all know that you can write it as some copy of the affine line C and quotiented by a lattice. So you have the usual picture here. And of course, this does not work. That's the first remark. This does not work over the p-adics because lattices are not discrete. If you take a lattice such as ZP, basically, it's clear that you have 0 as an accumulation point, and the theory fails quite badly. But there's actually a way around this, which is, say, John Tate's idea, is to use not like a complete uniformization, so to speak, but only a partial uniformization, by which I mean that you, you can start with C modulo your lattice, and you just compose maybe with the exponential 2 pi I, that like it's up your period 1, and you now get another quotient, like C star, quotiented by the action of some complex number Q. And of course, so it's kind of a partial uniformization because C star is no longer simply connected. But still, it's some nice pictures. So we had this picture of a lattice before. So now I have the picture that I drew here. So C star is, of course, just P1 of C with infinity and 0 removed. And if you want to look at the quotient, so you should draw a picture when you see the action of Q, of the multiplication by Q, which I basically did here. And so I draw two disks, one centered at infinity, one centered at 0. And what does the multiplication by Q do? It just sends like everything that's outside the disk around infinity inside the disk around 0. And it sends the circle to the circle. So when you do the quotient, you just glue the two circles and you find the usual like donut picture, which is to say exactly an elliptic curve. Okay. So that's for sorry, the elliptic curve case, and this actually works even over the p-adics, you can form the quotient QP star modulo Q to the Z for some Q with absolute value smaller than 1. And it's the set of Q points of an elliptic curve. And yeah, so this was really the basic idea of used by John Tate, and it was what motivated him to actually develop a full theory of non-Archimedean analytic spaces, the so-called rigid analytic spaces, in order for this quotient QP star mod Q to Z to make sense as a decent analytic map or through a uniformization analytic map. Okay. Of course, I should point out that there is some important difference between the p-adic case and the complex case. That's over QP, not all elliptic curves arise as such a quotient, only those with some special bad reduction that we call Tate curves. Okay, so much for elliptic curves. Let's now turn to some more general case. So how do we generalize the picture? So this is called Schottky uniformization. So with my elliptic curve, I had two disks, and I was sending one circle to the other circle. Now I take, say, G pairs of two disks. Maybe I should put the picture now here. Okay, so P1 of C, and I draw, say, this will be genus 2. So I have 4 disks, and they go by pair exactly as before. So I have some elements, say, gamma 1 in PGL2 of C, so Möbius transformation. And it's supposed to send the complement of the disk D-1 to the interior of the disk D1. Okay, and each of the gamma i's behave this way with the disk. Okay, and of course now, so it's a picture very similar to that of the elliptic curve before, except that we have more disks. And of course, if you do the quotient, the action by the gamma i's now, you just, the circles around D-1 and D1 get glued together. Same for the circle around D-2 and D2. And you find now like a surface, a Riemann surface with 2 handles, so a genus 2 surface. And this works for any genus G. Okay. And oh yeah, so, but I didn't, so what you see here is basically a fundamental domain, meaning P1 of C minus the 4 disks. And we would like to go to the uniformization. So what is the analog of C star in this picture? So if we have a fundamental domain, what we need to do is just like let the gamma i's act on the fundamental domain and see what we get at the end. So if you let the gamma i's act once on this picture, you basically find something like this. So some kind of a copy of the fundamental domain inside of all the disk. And if you let the gamma i's act once more, you find something like this, and so on and so forth. You get smaller and smaller disks, and at the end, you just get infinitely many points, but still that are basically in some quite controlled and quite small set, outside of which you control the action of the gamma i's. So that's how Schottky uniformization works. And so let me sum this up here. So we have this properties. The set, I consider the set gamma to be the set generated by all the gamma i's. So it's not difficult to see that it's a free group of rank G. And that's what we call a Schottky group. And there are important properties. The first is that there exists a compact subset, which is what remains when you remove all the smaller and smaller disks that we had before. So it's a compact set, and the group gamma acts on the complement of this compact set in a properly discontinuous way. And the quotient is a compact Riemann surface of genus G. Okay, some other important properties. So every compact Riemann surface of genus G rises in this way up to something you may need to replace the disks by slightly more complicated domains that are bounded by Jordan curves, general Jordan curves, instead of circles. It's not difficult to prove this. You usually start with your Riemann surface of genus G. And so you look at the homology. So it goes by, you have like G pairs of generators, and you choose one generator, like one pass into your surface for each pair, and you cut along this pass, and you find a picture that's very similar to this one, the one of P1 of C, with like G circles, G disks removed, and you get back to your Schottky picture. And the second important thing for what I want to do is that David Mumford in 1972 showed that this theory of uniformization may be adapted to the non-Archimedean setting. And as before, in this way, using this kind of uniformization, we do not find all the possible curves, only some of them, which are called Mumford curves. Just like for elliptic curves, we only get the so-called Tate curves. But still, we have like many curves that arise in this way, and it's a very nice behaving family. Okay. And what I would like to explain now is that actually those two different settings, the complex setting, the non-Archimedean setting, it's you have much more than just an analogy between the two of them. It's really kind of part of the whole theory that could be developed just in wider generality in a theory that encompasses in a natural way complex analytic spaces and p-adic analytic spaces. And it's quite striking that Mumford really defined it by analogy. If you look at the introduction of his paper, it begins with some kind of review of the different possible uniformization of complex analytic spaces, and he said, well, okay, the only one that will be able to make work in the non-Archimedean world is the one by Schottky, and then he goes on actually doing it. And I believe that there's really a much deeper, and something deeper than an analogy between the two. And so, in order to say things properly, I would like to tell you a bit about what's called Berkovich spaces over Z, so over the integers. Yeah, here we go. Let me start right away with the definition. So it goes like this. So the analytic space of dimension n over Z, in Berkovich sense, is, so as a set, you just take all the possible multiplicative seminorms on the ring of integers with n polynomial variable added. Okay, set of multiplicative seminorms. I give an example right after that. I just want to give the general definitions first. And so you can undo this set with a topology, weak topology if you want, so meaning that all the topology for which all the polynomials give rise to continuous functions. Okay, so now we have a topological space. Of course, we want more than that. We want a locally ringed space. And here it goes. So we use the Berkovich define the structure sheaf. So first, to every point here, we associate what's called a complete residue field. So it goes as for scheme. So if you have a multiplicative seminorm, it has a kernel. Since it is multiplicative, this kernel is actually a prime ideal. So you can mod out your ring of polynomials by this ideal, and you get a domain. You can look at the fraction field of this domain, and you can complete. And this way, you get some evaluation map. Okay, and now you can use those evaluation maps to define the function. So it goes like this: to any open set of the Berkovich space, you say that analytic functions are like some recipe that associate to any point of view an element f of x, to any point x of view an element f of x in h of x. And then you remember that you are in some analytic world, you want to add some analytic condition, and you require that f is locally a uniform limit of rational functions without poles.
Sorry, Jérôme, you complete the quotient in the definition of h of x, you complete the quotient with respect to the norm given by x, yeah?
Yeah, so there's actually a semi-norm associated to x.
Yeah. Yes.
Now, when you, of course, mod out by the kernel, it becomes an absolute value on the domain and on the fraction field, and you complete with respect to this absolute value.
So am I right that this completion is nothing more than just R? Or not? The norm was with value to R, right?
No, it depends.
It was not. Bar X is a norm with variation what? I'm sorry.
Yeah. Okay. Let's look at an example. I get back to the definition afterwards. So this I wanted to give an example of points, so that the next slide. Let's do it now. So first, we want a multiplicative semi-norm. So here is an example. You take a point t in C to the end, and so you want a multiplicative semi-norm on the ring of polynomials. So you start with a polynomial, you evaluate at the point t, and then you compose with the usual absolute value. The one I denote with the subscript infinity is just the usual absolute value, okay? And so then what is the completed residue field here? So here the kernel is just like a capital T minus small t, right? So the kernel is just, what do we get here? What do we get here? It's something like z adjoint t, but endowed with the absolute value that corresponds to the one you used here, so endowed with the usual absolute value. So here as a completion, we get either C or R, depending if our small t is in R or in C, okay? But then you could also do the same thing with some element in QP, right? So you evaluate at the QP point and compose with the absolute value, with the p-adic absolute value, okay? And then, of course, your residue field here, it's just basically z. You take the fraction field, so basically you go to q, and then you complete with respect to the p-adic absolute value, so you get a residue field that is qp.
Yeah, I see. Sorry.
Okay, that no, thanks for. Okay, so this way, and okay, I get back to this slide to this slide later, but. Okay, so you have all actually the different residue fields that can be a lot of complete fields with different residue characteristics and even different characteristics. And when you have them, it gives you a way to evaluate maps. And so when there are complete fields, you have a nice notion of limit. So it gives you a way to speak of uniform limit of function. And so we say, I mean, Berkovich says that an analytic function is something that is locally a uniform limit of rational function without poles. So it should be reminiscent of what happens in the complex setting. In the complex setting, if you look at a rational function without pole, we know that it's a holomorphic function. And we also know that holomorphic functions are stable under taking uniform limits. So we basically, if we start with this definition in the complex case, we just get back the usual holomorphic functions. Okay, so these two slides, so yeah, I'm sorry, it may be like quite abstract, but actually I'm not going to need them in what follows. Just to tell you that there are like very general definition for Berkovich spaces. So I stated them with Z here, but you could even state it, and Berkovich did, for arbitrary Banach rings, just to tell you that it's something very, very natural and very general, and that I want to specialize in my setting. But you can basically forget about the definition for the rest of the talk. So let's back to the example. Let's get back to the example. So as we already saw, if you take a point in C to the n, it gives rise naturally to a semi-norm, so to a point of the Berkovich space. if you start with a point in QP, it also gives rise to a point in the Berkovich space. So you have in the same space C points, QP points, etc. But of course, this is a bit weird because here, the seminorm I wrote, all of them have non-trivial kernels, like, generated by T minus U or T minus T. And but of course, you can also consider like true norms if you want, true absolute values. And this is what happens, something specific to the p-adic or to the non-Archimedean case. You can consider supremum norms on closed polydisk in QP. So this is something very specific to the non-Archimedean setting. If you look at a closed polydisk and the sup norm on it, it is multiplicative. So it is a multiplicative norm. So it gives rise to a point in Berkovich sense. And this is basically this is why there are more points inside Berkovich space than only the point in the field that you started with. And this is the reason of all the good topological properties that Berkovich spaces have. So for instance, so there is a picture in the next slide here. Maybe you saw this kind of picture before if you ever heard a talk about Berkovich spaces. And so one nice property is that Berkovich spaces are path connected, and which is, of course, is a bit disturbing since we started with something like QP, which is itself totally disconnected. So how does it work? It's really because of those additional points that correspond to this that we added. So for instance, if we start with the point 0 that's downstairs, how are we gonna draw a path between 0 and the point 1? We just use disks. So to each disk, using the supremum norm, we can define a point in the Berkovich space. So say we start with 0, we can somehow identify 0 with a disk of center 0, radius 0. And now we let the radius grow. So disk of center 0 to radius 0 to disk of center 0, radius 1/2, say, and all the way to disk of center 0, radius 1. Okay, very good. So it's already like a segment inside the space. But now you are at the disk of center 0, radius 1. But in the non-Archimedean world, we know that this disk of center 0, radius 1 is the same as the disk with center 1, radius 1. And then, so you can go down using another path, like a path going to 1, like assuming that each time your center is 1. So you go, so you let the radius grow to 1, and then you can pass, when you reach 1, you can pass from disk of center 0, radius 1 to the disk of center 1, radius 1. So you pass from 0 to 1, and you can draw paths in your space in exactly this way. Okay, so I don't want to spend too much time on those Berkovich spaces here, because we don't really know to understand the topology, but I still want to recall that they have a very nice topology. And okay, so back to my example before. So I told about 1, which was evaluation at a C point, 2, evaluation at a QP point. You could also evaluate in points in finite field. So FP or FP to the power n. So you evaluate at a point in FP, and then you compose with the trivial absolute value. Okay. So all are points, but for those example of points, you see that I mainly specialize the variables. So I should also tell you what happens with Z. So maybe the first example to deal with should be the space of dimension 0 over Z. And so how does it work? So we are looking at semi-norms defined on Z. So this is very reminiscent, of course, of Ostrovsky's theorem. So what I'm going to draw here is like some kind of picturesque version of Ostrovsky's theorem. So the point of the Berkovich space of dimension 0 over Z are basically all the possible absolute value of Z. So it goes like this. So you have the absolute value subscript 0 in the center. It just, so the trivial absolute value. Okay, and then I draw one branch, one for the Archimedean absolute value, and so one for this absolute value and the powers of this absolute value. And for each prime number p, I draw also a line for all the powers of the p-adic absolute value. And at the end of the picture, so the last point is kind of like the periodic absolute value raised to the power infinity. So like absolute value of P becomes 0. So it's just like you compose Z with the reduction mode P and then with a trivial absolute value. So you get some kind of a tree-like picture like that. Okay, and the thing is that if you have a Berkovich space of dimension n over Z, you have a map to the Berkovich space of dimension 0 over Z, just forgetting what you did on the variables. And we can describe in quite an easy way the fibers of this map. And this is how it works. So for instance, if you look at a point in the Archimedean branch, the fiber of it is basically like a usual space C to the n, okay, modulo some action of complex conjugation. If you look at a point inside a p-adic branch, what you get is the fiber that you get is a usual Berkovich space. So in dimension 1, it has this tree-like structure that we saw in the slide before. So that's what you should remember, kind of topology speaking, about Berkovich spaces of a Z, that it maps onto this like Ostrovsky's tree, and all the fibers are either complex analytic spaces or p-adic analytic spaces, usual Berkovich spaces. But all this is put together in a very actually natural way. That's also the reason why I gave the definition at the beginning. I mean, I didn't want just to say that it is a space where you have complex analytic spaces and QP analytic spaces. And because you could have thought that I was doing some kind of weird gluing or I don't know what. There is no gluing involved in the definition. It's a direct definition in terms of the ring Z, which happens to have a description in those terms with different fibers. It's like just a natural object at the beginning. So that was for the space. And something else you should remember about the analytic spaces of a Z has to do with the functions on those space. So the functions are like this. They are basically what David Harbetter called, so for different reasons, he considers similar functions, he called them convergent arithmetic power series. And I like this name because I think it conveys quite nicely the idea. And so I'm going to give two examples. So what you should think about functions on Berkovich spaces of a Z as functions with some analytic features and some arithmetic features. So for instance, if we look at the relative open union disk of a Z, the function we get are exactly those that I wrote down here. So there are power series with coefficient in Z, so that the arithmetic feature, but with complex radius of convergence, at least one. So you require some convergent conditions. That's the analytic feature. So that's a global ring, a typical global ring. And now here is an example of a typical local ring. So I told you here precisely a local ring at which point it is, but we don't care that much. So I want to say that this local ring is made of functions that are a power series with coefficient in Q. So you have some kind of an arithmetic localization, which means that you don't consider power series with coefficient in Z, but with some localization in Z. And for each function, you only allow finitely many prime numbers in the denominators. Okay, and then you have analytic conditions. So here labeled 2 and 3. So you want the complex radius of convergence to be positive. So it's a typical analytic local condition. And also for each prime number P that divides the denominators of the function, you want the p-adic radius of convergence to be positive. So this is a typical example of a local ring over Z. Okay, so that was for the picture, and then the function, this analytic arithmetic kind of function over Berkovich spaces of Z. Okay, and now, okay, one last slide on this to tell you about properties of the Berkovich spaces of a Z. I'm going to be quick about those. Just want to tell you that there are spaces that also that not so much studied that have a quite nice property, like the properties we would expect for basically any analytic space, and that we can work with them in quite a nice way. So Berkovich proved in an even wider generality that such a space is Hausdorff and locally compact. And then yeah, a bit of shameless self-advertising. So the space is known to be locally path-connected. It has also nice property about so the structure sheaf is coherent, etc., etc. The local rings are Noetherian and Celian excellent, whatever you want them to be, and also some cohomological vanishing properties. So just a list to tell you that those spaces behave well, and probably if there's something you want to do with them, the machinery has already been developed. Okay, so now let's go to my next part. So I want to say something more maybe about Berkovich spaces over Z. That for me, I mean, the way I think about them, and actually more and more, is that I'm pretty sure that there are very nice kind of analytic moduli spaces. So in some sense, if you have like some moduli problem of an analytic nature, but in quite a broad sense. I mean, some moduli problem that makes sense over C, over complex analytic varieties, or over p-adic analytic varieties for any P, then probably you have something that would make sense over Berkovich spaces over Z in an even more general setting. And probably Berkovich spaces would be a nice way to encode or to provide a solution to this moduli problem. And I don't have so many examples at hand, unfortunately, but here is one. That's the example of Schottky spaces over Z, because this Schottky uniformization, I told you before that you can do it over C, and you can do it, and Mumford did it, over also the non-Archimedean spaces. Okay. So let's try to do that. So how should we proceed? So I will first speak about what's called the so-called Koebe coordinates. So it's a way to encode like some Möbius transformations, hyperbolic Möbius transformation actually. So we start with a complete valued field that is either Archimedean or not, it doesn't matter. And so we now have some hyperbolic Möbius transformation. So it's some element of PGL2. So we could try to encode it by, I don't know, like 4 coefficients, or not. But for what we want to do, it's much better to do it in another way, that's the so-called Koebe coordinates. So we have one attracting fixed point, one repelling fixed point, and also, so this element has 2 eigenvalues. And of course, you are in PGL2, so those 2 eigenvalues are not well defined. They are only defined up to homotopy, but the quotient of them is actually well defined. And so you know the beta, the quotient, I mean the one of the 2 quotient that has absolute value smaller than 1. So to get back to my example with the elliptic curve, then the multiplication by Q. So the fixed point, attracting fixed point would be 0, repelling fixed point would be infinity, and the beta would be the Q. So it's just a generalization of that. Okay, and of course you can go the other way around. If you know alpha prime, you know beta, you can write down explicitly what the Möbius transformation is. You have some explicit matrix like this. Very good. Okay, so now that's a way to express in coordinates our gammas. And so yeah, so remember that we had for the Schottky groups, they were generated by G elements that I labeled gamma 1 to gamma j. Okay, and that's the way we are going to define the Schottky space. So basically, we want to define all the possible gamma j's that give rise to Schottky groups. So Schottky groups correspond to the groups appearing in the Schottky uniformization we talked about before. So that's exactly it. So you have like a bunch of alpha, a bunch of alpha prime, a bunch of beta, and you cook up matrices, Möbius transform with them as before, and and you only keep in your space all the elements where the group that you generate using those matrices when the group is a Schottky group. Okay, so it goes like this. So there's something, yeah. A small subtlety here is, of course, we are in PGL2, and we have we somehow want to restrict the degree of liberty we have, but fixing 3 points to be 0, infinity, and 1 up to conjugacy. This is always possible. So this way we have 3 variables less to deal with. So that's exactly the way it works. So you define to be so the Schottky space is a space of point like x3 up to yj over any field if you want, either C or R or QP or FP double parenthesis T, what you want, such that when you cook up a group using those coordinates as Koebe coordinates for G matrices, the group you get is a Schottky group. It's like some kind of uniform definition for a space over Z. Okay, and now came something that was really kind of a surprise for me. So this is part of a joint project with a former postdoc of mine, Daniele Tucchetti, in that the Schottky space is, so Berkovich, as a Berkovich space of Z, is a connected and open subset of some affine Berkovich space over Z. I mean, I said it was quite unexpected for me. I mean, when I saw about that, like Mumford's definition was like very clever, of course, but it was like really an analogy between something complex and something p-adic. Okay, and then I mean, I saw no reason was like it should really be the same definition and not something you copy from one side to the other. But then it turns out that if you actually use this definition here and you just keep in your space the points and that give rise in those two a pretty different sense, then the space you get has some analytic structure. It is an open subset of some affine space over Z, affine analytic space over Z, and even a connected space, actually. And yeah, so I'm not going to go into the proof of it, but the proof is actually quite natural. Just, yeah, let me say it with 1 or 2 words. So you start with a point in the Schottky space. So meaning basically you start with J matrices that generate your group. And with those J matrices, you know that there is some associated Schottky figure. Maybe not with those generators, but probably in a way you can control. So this is part of the problem. So I don't want to say too much about it. But so say that your generators correspond to generators that send disk to disk in a nice way, as we saw before. Okay, and then you move your point a bit in the affine space. And if you move your point a bit, you need to understand that the figure you add with those disks, you should be able to find new disks quite close to the disks before that that also behave nice with respect to those new generators you add. So if you change a bit the generators of your group, you just change a bit the figure, and it just steals some figure with disks, so it's still a Schottky group. That's more or less how it works. And and this way, you get the fact that it is an open subset, and even the connectedness quite easily. Okay, sorry, maybe there are too many things appearing on my screen. I don't know if you see them or not, but should get rid of everything. No. Okay, yeah, never mind. Okay, so that's the definition of the Schottky space. And it's more than a space. It's the thing is that now you can do all the Schottky theory with this space here. So what do I mean by that? So this slide may look a bit complicated, so you should probably only look at the diagram downstairs. So we have the space SG downstairs, the Schottky space. And if you take one point in this space, so over it, you want to look at the corresponding universal cover or partial universal cover. So it sits inside P1, okay, by definition. So let's just consider the product of SG, the Schottky space, with P1. Let's do that. And okay, and we remove in this, for each point now, we have a so-called limit set, the set that we get when we remove all the disk we have in the big picture. So for each point, we have a limit set. And over each fiber, we will remove the limit set. And the nice surprise is that the set we remove this way is happens to be closed. So which means somehow that all the limit sets behave continuously over Z. So even when you pass from C to something non-Archimedean, you have a continuity of the limit sets. So you can remove all the limit sets at once and find some open space. And on this open space, you have some kind of a universal Schottky group defined. So it's a free group like defined in the third line of my slide. And this group acts in a free and properly discontinuous way on this space. And if you look at the quotient, you find like the Mumford curves and the Riemann surfaces that were Schottky uniformized. And the nice thing is that so the three arrows in my diagram downstairs are actually analytic arrows. So they are analytic morphism in the category of Berkovich analytic spaces over Z. So it's really something so that you really have a uniformization, a global uniformization at the level of analytic spaces over Z. So you have all your family of Mumford curves, Schottky uniformized curves, and a global uniformization that is a global analytic map in this setting. Okay. So you can already do the theory globally over Z directly without having to worry if you are over some Archimedean or non-Archimedean valued field. It works in exactly the same way. Okay, and to finish, let me say a word about a few applications or possible application of the theory. So unfortunately, the application I'm going to talk about are not mine. But I believe that it's possible I mean, having this geometric construction of the Schottky space in mind, I'm pretty sure it's possible to push maybe further the application that were already done on. Okay, so I would like to mention something that's maybe not so well known. It's called like a Teichmüller modular form. So how does it work? So quite quickly, let's start with MG, so the moduli space of smooth connected proper curves of genus G. So you have a universal curve over it, pretty much by definition. And you can, you have, so over MG, you have a nice line bundle that you can construct by pushing down like the Hodge bundle of the universal curves and taking the maximal exterior power. So this is a line bundle. And we can define Teichmüller modular forms to be global sections over MG of this line bundle, or maybe some powers of this line bundle, tensor powers of the line bundle, if you want to put whites. Okay, so it may look as some kind of a fancy definition, but it's actually very reminiscent of what we do for Siegel modular form, for instance, except that we don't consider MG, but AG, the moduli space of principally polarized abelian varieties of dimension G, but it goes the same way. And of course, the two kind of modular form are related. So you have a Torelli map, Sandiger curve to a Jacobian, and so which gives a map from the Digel space of the Digel modular forms to the Teichmüller modular forms. Just said that if you know how to evaluate something like on an abelian variety, you can give a value to any curve just by considering the value it takes on its Jacobian. And okay, and what does this have to do with the theory of Schottky spaces? It goes through expansions. Actually, there is a well-defined notion of so-called Fourier expansion for Zygon modular forms. And Takeshi Ichikawa defines some expansion map for the Teichmüller modular form. So which goes into this ring here, which may look a bit weird, but which is actually very related to the Schottky space and the Koebe coordinates. Actually, you should think of the xi's as the alpha i's and the alpha and alpha prime. So the fixed point repelling or attracting fixed point that we had before. So we have 2G of them, and because we inverse the xi minus xj, it means that we want them to be distinct. And then you should think about the yi's as the beta, so the quotient of the absolute values. And you remember that we chose them to have absolute values smaller than 1. So in a geometric version, it said that you can construct power series with them. So this should be a ring naturally associated to this Koebe coordinate situation. And actually, Ichikawa didn't use the Schottky spaces over Z. They were not defined in 1994. But he used something very similar. And he certainly used a Mumford uniformization that he generalizes to the kind of rings that you actually see here with those variables. And if you are familiar with the theory of Zygon modular form, for instance, you understand why it should be interesting to have those uniformization going on. And just in one word, how do we find expansions? The thing is, so if I go back to the previous slide, so we have this lambda. So I said that was a line bundle. Okay, so a line bundle, you can trivialize it. And if you trivialize it, now any section of lambda corresponds to just some global section of your space. Okay, so now we would get some global section of maybe over mg. So maybe it's not so convenient, so we can restrict mg to the locus of the uniformizable curves, so basically to SG. And then we have a uniformization, and then we can look at lambda or the Hodge bundle. And here we have, hopefully, we are over an affine space, and hopefully we have, and we do have, a kind of canonical trivialization of the Hodge bundle. And using this canonical trivialization of the Hodge bundle, so we know how to associate to each modular form just something that an element of basically a function on SG. So Ichikawa in his setting did not have function on SG, he has function in this ring here, but with the theory I described before, we could somehow like upgrade this expansion map to something with values in O of SG, which basically mean that you provide additional convergence condition. So remember I told you at the beginning of the talk about this convergent arithmetic power series. So now the evaluation map could map into arithmetic convergent power series. Okay, and something nice you would like to do is also to relate those expansion to the Fourier expansion of Zygon modular forms. And Ichikawa does this too, relying heavily, of course, on Manin and Dülfeld's paper about period of periodic Schottky groups, because this paper does exactly what we need, meaning relating the uniformization of a curve to the uniformization of its Jacobian. Okay, and next, what we would like to do is to use those to study the Schottky problem, so of characterizing Jacobian varieties among abelian varieties. Okay, and in a last slide, I would like to get back to and to present some results is a genus 3 case. And here the main player is going to be a Zygon modular form called Chi 18, so white 18. It's the product of all the theta null vector with even characteristics. And here you already see something interesting about those Teichmüller modular forms, because when you pull back this Ziegel modular form Ki18 to the Teichmüller modular form, it becomes a square. So it's a result due to Tsuyumin in the complex case and Ichikawa over Z. And this also has a nice application. So it already tells you that this result tells you basically that this Ki18 is a square when you restrict to the locus of the Jacobian locus inside the moduli space of abelian varieties. And there is a very nice application of this derived by Lachaud, Ritzenthaler, and Alexey Zykin. And it goes this way. So the setting is the following. You look at a subfield K of C, and you look at principally polarized indecomposable abelian threefold. And you require that this one is isomorphic to a Jacobian over C. And the question is whether it is or not isomorphic to a Jacobian over the smaller field K itself. And the answer is probably you could guess it by looking at the theorem above, and I basically proved already one direction that if this is a Jacobian, then this Ki18 is a square, and also the other way around. Okay. And so I would like to finish my talk with this nice result. So of course I would like to have discussed all of this with Alexey himself, but unfortunately this is not going to happen. But I mean, I think that also thinking about this question is also a very nice way to remember him. So thank you for your attention.
Okay, thank you. Oh, wow. Such a nice photo. Thank you, Jérôme. And are there any questions?
Yes, I would like to ask. There is a solution of Schottky problem for this Jacobian inside of abelian varieties by Schrödinger and so on by means of tau functions, Kadantsev-Petriashvili equations from mathematical physics. And is there some relation with this, or it's a completely different approach?
Sorry, could you say again who the solution is due to?
Oh, it's more than 40 years ago. It's short and so on. That, for example, you consider them some tau functions constructed by theta functions, and so that it should satisfy the Kadantsev-Petriashvili equation, and then it's Jacobian of the curve. It's written, for example, in appendix to it's in Russian, but maybe in English. So to Mumford book of theta functions and so on. So, but it's really in terms of mathematical physics, but it's completely solved. This is
yeah. No, so okay, so I'd rather be careful on that one, but I think this is pretty related. So there are also some papers by Ichikawa that are devoted actually to the relationship between those Schottky spaces and these KPZ equations. So it's no, I think it would be dangerous to me to say much more about this topic, but I'm pretty sure that Ichikawa worked out the relation properly. And I should have a look at that more carefully and get back to you maybe. But, yeah.
Maybe I have a question. Hi, it's Christophe.
Oh, yes.
Hi.
Hi, Jérôme. Thanks for your talk. It was very, very interesting. I was wondering, at some point you say that you can make a bit more precise this expansion formula. I mean, you have the map. I think it was 2 slides ago or something like that.
Yeah. This one probably. Yeah.
Exactly. I mean, and now, I mean, you say that you go a bit more further than Ishikawa, and you give even like additional convergence conditions, right?
That's right. Yeah. Yeah. Okay. So this is not like from what we did with the Schottky moduli space, it should be very easy to do it. We basically just need a map to the moduli space. The thing is that Berkovich spaces over Z are not well studied. So we basically what we need is to know that there exists in a strong enough sense a moduli space of curves as a Berkovich space over Z with a nice property that you should have a map from SG to MG. Once you get that, it's pretty easy to have Ichikawa's expansion map. And I think it would actually make the proof of, his proof clearer. Of course, it's arguable, but I think it would. Probably he has exactly in mind this space, like a space where all the uniformization are put together, but without like the right analytic tools to define it. And so his proof is kind of complicated doing, redoing the construction by Mumford over some more complicated ring and so on. And afterwards comparing the different definition, whereas we could do it directly in full generality, I guess.
Okay.
So yeah.
If I can, I was also wondering if at some point, like going a bit further, refining maybe all these, you could even like produce new Teichmüller modular forms that would not come from Spiegel modular forms.
Yeah, that's definitely a question I wanted to investigate, but I didn't have much time to do it. It's of course it's a bit subject, but so we at some point with Daniel we decided we just write down what we know how to do first and then try to concentrate on all the questions. But I think that's something nice. We have now like analytic quite flexible tools, those Berkovich spaces, and so that's exactly as you did. I would hope that it's possible to do something with that to construct more Teichmüller modular form, but I don't want to say anything more precise right now. It's quite a long term goal, I would say.